So we were here, we were trying to understand each one of these things about the term symbols, and in this context the Russell-Saunders coupling was the thing that was discussed in detail, and how to derive a term symbol that I told you last class, last to last class, and several 2-3 classes that we have discussed. LNS, how to write term symbols, and the Clesp-Gordon series you need to follow. You don't have to consider the closed shells. These are the points we already discussed. So beyond this, by ignoring closed shells because they do not contribute to any angular momentum, then sodium, so finding the configuration for sodium, fluorine, and excited state of carbon. These things, so these were already discussed in offline classes, and so we are, so to find, okay, so these were the different states that we found by solving. So you have to need to get back to the take pen and paper and then do it by yourself. Then only you will understand. If you have any problem, you can ask me. And the basic idea, how it is easy to write L plus S and those things, say that this couples with that, but how exactly it couples, that is, if you want to really understand that, then you need to understand that electrons behave as small magnets, okay, as a tiny magnet, and each of these you can treat like the spin generates a magnetic moment, so that is to be considered as one tiny magnet, and the orbital motion also generates a magnetic moment, so that becomes another tiny small sized magnet, and then it is the interaction of the two magnets. That's how you have to consider the things. So the interaction is in this manner, so it is always a magnetic interaction. Whenever we talk about spin orbiting interaction, it is the magnetic interaction between taking spin magnetic moment and orbital magnetic moment, both of which are, of course, I told you earlier that each of these magnetic moments are proportional to the angular momentum. So spin up, spin down, this is the magnetic field, and so aligned with the field or opposed to the against the field, you can have two type of orientation, so energy can change. So this is the basic ideas of spin orbit coupling, how the interactions takes place. Okay, don't only memorize the steps that L plus S, L minus S, whatever happens, how it happens, you should have a 3D visualization. Okay, so it is a magnetic interaction between the angular momenta, and that's what we were specifying. L and S generates two magnetic moments, mu1, mu. This due to and this is due to orbital motion, and this is due to the spin. So we are treating these two as tiny magnet, these two entities, the two magnetic moments, as two originating from two tiny magnets, and then the interaction gives you the overall thing. So in this case both are pointing in the same direction, so L plus S, and you have so that is one thing, and L plus L minus S, so if they are pointing in the opposite direction, L minus S, this is the situation that we were talking about. So high J values, this will be of higher energy, because considering the applied field is uh, H, and so this is the applied magnetic field, and in that, if something gets aligned, so electrons will have momentum. So you can see in electron the direction is always opposite to the angular momentum. The magnetic moment is always opposite, pointing in the opposite direction to the angular momentum. If you take the case of proton, then it is the reverse thing, it will be always aligned. So to the angular momentum. So that is, so in that manner high energy comes out because you have a components of both the vectors magnetic moment pointing in the opposite direction to the applied field, whereas in this case at least one of the components, the spin spin magnetic moment, is pointing in the direction of the field. So there is less energy in this system. So that was the idea that were earlier considered, and based on that we had, so these were the things already discussed. I'm just giving a quick recap of what we have done. And so less than half full, J will be so lowest value of, so smallest value of J will be lowest in energy, and it will reverse for the if the if it is more than half full. So that the reason, because is that here you can treat it as loss of one vacancy. If you have number of vacant after the half filling, it is better to consider it as a vacancy for the electron, and that vacancy behaves uh, that vacancy you can say a hole, which is which can be treated as a positively charged things. And so now the orientation of the magnetic moment will be different as considered in previous case. And so in that case J with the largest J value will be lowest in energy, and vice versa. So these things were discussed, and five so P2 configurations, if you go on writing for Px, Py, Pz, the ML values, uh, individual orbitals, then you can get 15 microstates, and number of microstates can be obtained by this. Okay, and if you have so for P2 configuration you can simply substitute. So n is the E is the number of electrons, and n is the number of possible orbital positions. So that's an easy way to find out how many states could be there, and then you can write all these uh, expected uh, uh, things, expected positions of the electrons, and so. So if it is more than half filled, you can treat it as whole. The vacancy can be so n minus e. You calculate n minus e, and that is becomes unoccupied side or holes, and that equivalence continues. So P4 or P2 both will have similar profile. So you calculate 6 substitute. So if it is a P4 situation or P2 situation, you get 15 microstates in any case. And so either way you treat it, you get the same result. Similarly, D1, D9, F2, F12 will have same number of microstates. So that is the microstates. And if you have, you can also think for, if you have multiple unoccupied orbitals, then you need to consider from the spin and from sorry from microstates from individual orbitals S1 P2. So if you have say a configuration S1 P2, then you consider both from S1 how many you can get, from P2 how many you can get. So that takes you to this, that there should be 30 microstates available. So these different ways in which you can arrange the electrons is your microstates. And then ML values, ML means that you have that many different orientations possible for L, the orbital angular total angular momentum, orbital angular momentum. And similarly the total spin angular momentum will also have 2s plus 1 number of ways to be arranged. So we were here considering writing the P2 configuration. Here we are taking advantage of that fact that plus and minus plus sign that we have is, we can assign this for spin. This is up spin, and this minus sign is for down spin. So that's how it has been written, up spin, down spin. And then you can arrange the ms and ml values and get this kind of table. If you write this, so So in this way, the description is shorter and becomes easier to collect because when you go to D2, it will be 45 microstates. So let's see how we do this. Now you have to find the maximum, start with the maximum ml values. So that is plus 2. That is when L is equal to 2, you can have the maximum ml as plus 2. And then you start finding the maximum ms for the system. So plus 2 means that both the electrons are in the same orbital, having a plus 1. So maximum possible ms is 0, and so the possible values all you can write plus 2 to minus 2, and so you can go on eliminating the microstates with from plus 2 to minus 2, having ms0. So ms0 1 plus 2 to minus 2 you can arrange, and so if you look at this, the red one, you are getting all of them. So this red ones you have to eliminate. So eliminate all these, and the new table. So number of such microstates that we have substitute is 5 into 1. S is equal to 0, L is equal to 1. So F, so 5 microstates indicated by red belong to 1D. L is equal to 2. So capital L is equal to 2. So D, and because they are singlet, 1D. So that's the possibility. In the next, now you take the next ml, highest ml value. So next ml is plus 1 and possible. So you write, and the maximum ms is 1. So this is the way you start working on it, and the possible values are this, and for this you have 3 ms values as well. Possibilities are this. So now subtract, eliminate all those combinations of ml and ms corresponding to this. So eliminate all the blue shaded region. So this, identify it, see this, okay, blue ones. So eliminate all these blue things, and so these belong to the next. So capital L is equal to 1, so it is the p state, and 2s plus 1, s is 1, so 3. So it becomes 3 into 3 and 9 microstates, and these 9 microstates. So you can cross check that whether what you have written and what you are expecting is matching or not. 9 microstates you must get. So 9 microstates here you are getting for 333 for each one. Plus 1, and when ml is plus 1, you are having 3 possibilities for ms. So you have 3 possibilities for L is 0, and similarly 3 for L when ml is minus 1. So we are left with only one microstate, so that belongs to 1s. So all are accounted for. So this is an easy way to find this thing. Next, we also thought of how do the energies. So for the carbon, so greatest multiplicity and highest value of ml will be the ground state. So yeah, so when you have, so that is how we find, that's already discussed. So S1 P1 configuration. So instead of P2, now suppose if you have S1 and P1, 2 electrons, but one is in S, another one is P1. So here it is important to note that 0 plus 0 minus and 0, this both both have to be considered as two different terms. In previous case, when both the electrons are in the same orbital, then we discounted only one of them was considered to be distinct. And so this is an important point. Different microstate treated as a different microstate, because when one electron is S, another one is P. Okay, and that's how you are arriving at total L value as 0, ml value as 0 components. So ml components, ml is 0, so that you are arriving at through by this consideration. So p orbitals, p can have plus 1, minus 1, 0 and 0. So 0 is coming so all these considerations have to be taken place. So corresponding to this, there must be some orbital which has to, so, and corresponding to s also you will have 0 l value. So ml 0 means when we are writing as overall 0, that means one is in s orbital and the one is p orbital. So we, these are these energy states that we are defining and their relative positions that we assign. All these are follow can be done in accordance to Hund's rule. So there are three Hund's rule to be followed. First one is very simple, of that one of highest spin multiplicity. So any configuration, so this we have already discussed previously. So maximum multiplicity, you are having parallel spins, there is exchange energy which stabilizes the system. Then comes the Hund's second rule, which says that if two or more terms are share the same max spin multiplicity, then the ground term is having the highest, is the one having the highest value of L. Okay, so for example, if you have P4 for F, so the one having the higher value of L is lower energy, and this consideration comes from the picture, that is, if you have higher L, that means for a P, let's say for P2 configuration, that means uh, when L is equal to plus 1, 0, minus 1, so that means when we are having maximum value, when L is equal to 2, both the electrons are having in the same L for both electrons, and that means both are moving in, both electrons, and they are moving in the same direction. So this kind of thing helps in understanding, because so when this is the situation, both are orbiting the nucleus in the same fashion. If it is minus 1, that means electrons in orbiting the nucleus in a reverse direction. So when this is the thing, you know, there is a consideration that I discussed previously. Yeah, I have already discussed this point. Yeah, here, when this is the situation, the preference is given. So similar thing was discussed in previous classes also. So when you have this kind of situation, two different, one each, then you need to consider that uh, such in such situations high L can be obtained in this manner when both the L are having same. So plus one or something like that. So in that case, they are orbiting in opposite direction. Sorry, opposite direction. The two orbitals are different. So if they are circulating in opposite direction, they will the tendency to meet, the probability of meeting each other is less, and the repulsion will be minimum. So that's why such, when you have high L values, capital L is high, that term is lower in energy, and so D term is, in this case, lower, S will lie higher in energy, because in that case they will be moving in the opposite direction and the chances of meeting will increase in three-dimensional space. So that is the analogy that has to be taken here to understand this aspect. And then the point, next point was, so we were discussing the Hund's rule, and Hund's rule of, yeah, Hund's second rule was about it, about the value of L. So higher value of L, both the electrons are moving in the same direction, the chances of meeting each other is less, so like the repulsion would be less. That's this reason. Hund's third rule says that if they are less than half filled, the state having the lowest J will be lowest in energy. The subshells that are more than half filled, highest J will have lowest energy. So this is in the again the consideration that we have already taken into account previously, discussed already. with a different way of putting the magnetic moments. Okay, in few slides back we have discussed that, and so it is not difficult to find why high J value, lowest state with lowest J will be lowest energy, L minus S. When it is they are opposed to each other, they will be lowest in energy for the half filled orbitals. So that is the, so one by one, if you treat it like that, triplet state is lower in energy as compared to singlet. And so for the reason that we have spin-spin interaction, that is parallel spins, there will be exchange interactions, and so it will be exchange interaction that is lowering the energy. And overall, because electrons are fermions, the spin orbital, the combined wave function of spin and orbital wave function should be antisymmetric. And the antisymmetric thing, because the spins are same, psi space must be antisymmetric. It must be different to follow the Pauli exclusion principle. Then comes the second one is due to the orbit-orbit interactions. The first one, spin-spin interaction. Second point is about the, so when you are putting this is due to spin-spin interaction, and the second splitting that you are showing is due to the orbit-orbit interaction. So capital L's of higher L, and then gradually higher L value of lower energy, and so on. So that is what we have discussed already. So high L and low L, the two considerations are here. So both of all of these are interactions. So you can treat it as like treat one of them as a magnet and another one as a substance that has substance that has been put it in the magnetic field. So then you can easily calculate the energy by this given thing, magnetic moment into the field, magnetic applied magnetic field, that gives the interaction energy. So this is the term that spin orbit coupling, S dot L, capital, both the vectors that give you. So energy is something related to from electronic motion. So you take mu is the spin, electron spin is taken to be a tiny magnet, and orbital motion is taken to be the magnetic field, that is also a magnetic moment, but so that behaves as a tiny magnet. And you can assume, that the magnetic the spin magnetic moment is feeling the magnetic field of orbital motion of the electron. So sorry, the magnetic field produced by the orbital motion of the electron. So that way you can calculate the energy quite easily. And for the P2 configuration, we have three terms that we got. We can arrange them. So triplet, then two singlet states, amongst them L, 2, L, S, L is equal to so 0. So like that you can have three different steps. So this is how we predict the ground state energy. Okay, and that it succeeds in explaining this scheme of things works very well for the ground state, but it is sometimes difficult to predict in this manner the energy of the excited states. So this is the view. So when there is no electron repulsion, then all the P2 configuration, all the 15 microstates are having same energy. When you take into account electron repulsion or spin interaction, repulsion and spin interaction, you have separation into triplets, triplet state showing much lower in energy as compared to the singlet states. And further, it is the spin orbit interaction which is giving, so spin interaction, then you have spin orbit interaction which splits the thing. Okay, So this is how we consider. So this is the splitting pattern that you are getting: 5 microstates, 3 microstates, all for the P2 configuration, where we started from. We have already located their terms and 3pz, and if you apply magnetic field, it will further split in terms of this will in terms of mj. So if it is 2, you can have, so 1 2 3 4. So in magnetic field it will split into ml mj, sorry, ml, no, mj. Mj values of -2, -1, 0, +1, +2. So this is how you can write mj values. For this there will be 3. So this will be only, this splitting will occur only in the presence of, so here mj is equal to +-1, mj 0, and +1. So in this manner you can have, so this is happening uh, in presence of magnetic field. This splitting will occur in presence of external magnetic field. So to complete the things, you need to show all these things that can happen. So magnetic interaction, spin interaction, spin orbit interaction, and then like this. So determination of spectroscopic terms involves, so we have already stated in previous slides how to do this. So determine the total number of microstates, determine the possible values of L, then possible values of ml and ms, determine the Pauli's allowed microstates, then set up a chart of microstates, resolve the group microstates into atomic states. So these are the 6 steps where you can do this. So D2 configuration, you can get similar examples. Step 1, calculate the numbers, so number of microstates. So 2 electrons is to be arranged. They can occupy 8 different positions. So this is the factorial in 10 factorial divided by 2 factorial and 8 factorial. So that gives you 45. 45 microstates are possible. Apply Clebsch-Gordon series already given in previous slide. So once you do that, you get the values of ml +2 to -2, and so there are 5 acceptable solutions, ml. So this needs to be told. So what could be the maximum value of ml? So these are the things that you already know. Step 3. Then ml is equal to 4 is the highest, +4 to -4. Allowed transitions, since 2 electrons may be spin aligned or paired, so ms +1, 0, -1. So then allowed slides can be drawn, and we can follow the similar steps as we did for P2 configuration, and we will be able to find the microstates for each of the terms. So you need to tabulate all the possible microstates. So preparation, what are the precautions to be taken while drawing this? So you have to make sure that no two electrons in the same microstates have identical quantum numbers. And to count only the unique microstates, you do not have to duplicate it. So that is example that I had given to distinguish a P2 configuration and S1 P1 configuration. So that one is an example where you have to be careful. P2 configuration compare with S1 P1 configuration. So for P2 configuration, 0 plus 0 minus, 0 minus 0 plus, these are duplicates. So only one of them has to be considered from the both pair, because we are talking about the same electron, same orbital. Okay, so duplication has to be avoided while making tables and counting them. So only unique microstates is to be counted. So this was the for D2 system, different 45 microstates in one go. So you can start writing and you can generate all of them, or you can write a table just like this by indicating the plus minus sign or plus sign on this as superscript 4, indicating the spin. So these are the, you calculate the maximum ms possible, maximum ml that can go. So it can vary from +4 to -4. So +4 when ml values are +2, and -4 when both are -4. So both. So now what we need to do here, once you have made this kind of table, you can identify each one of them. So first term, when 3f term, so f is equal to 3, and so sp 0 1 2 3 spdf. So yeah, l is capital L is equal to 3, and ms, maximum value of ms is equal to 1. So total number of microstates you can calculate 2l plus 1 and 2s plus 1. Yes. स्टूडेंट्स आए नहीं थे, ऑफलाइन क्लास नहीं लेते तो ऑनलाइन ले रहे हैं. स्टूडेंट्स आए ही नहीं थे, 5-6 आए थे, मैं ऑनलाइन ले रहा हूँ. गिव मी 10 मिनट. तुम लोग निकलो नहीं तो मैं आता हूँ लंच. So that's how. Okay. So this is क्या मैं बोल रहा था, हाँ. So you can always cross check 12 plus, so L is equal to 3, 3 plus 3 to 2, so you can put it here. So this becomes 7 into S is 1, so 7 into 3. So total 21 microstates should be there for 3f term. And now you need to identify, so different, when L is equal to 3, you can, the range should be +3 to -3. So you take all the possibilities from each one of these, this crossed out red colors one, you can see. So this is the same thing. This table is now viewed in this context. So we are striking out all these terms which are here. So ml value, so from plus to L is 2 minus 1, so +3 to -1. So all of them you can take it out, and these are we have to cross out. So like that from the top of this. So all this, can you? जरा सा फैन चला था आवाज आती है. Okay, this one. So you need to cross it out. So all these, when you identify, they are 21. These are the 21 microstates. Next you move to the L is equal to 4 with S is equal to 0. So you will have, you can easily cross check 2L plus 1, how many microstates should be possible. So 9, and so 9 microstates, S is equal to 0. This is for the spin multiplicity, gives you one microstates only. So only so 9 microstates that you can easily identify from in the one slab here. So you just put it with a different color, and you can easily change the color. So strike out all these. This is the second one to be taken out. Second one to be taken out. So these are all 9 microstate to the of the 4. L is equal to 4. Similarly, you can go ahead and try to cross out all the L is equal to 1, ms 1, and so you will again find that it is 9 microstates, because yes, 3 into 3 is 9. So similarly, L is equal to 2, S is equal to 0, and finally L 0, capital S 0. So only one microstate that is lying here. So this is a stepwise manner you can perform this by yourself, and after writing a table like this, so in one page you are able to finish this part. There's another way to do the same thing. The one way I have already told you. So 45 microstates I am able to write in one, in a matter of 3 by 9 tabular format, and then identifying the microstates is easier. It is done. However, if you want to do it another way, there is another way to do it. You write all the ms terms first. So plus 1 plus 1 plus 1 you write first. Then once you have resolved all the plus 1 ms states, by symmetry you can say that there should be equal number of states for ms minus 1. That also you can write. So all are having downspin. So this is the visualization that you can write. If you find this way okay, then you can consider. So 10 plus 10 20, and then the other combinations with 25 microstates with ms is equal to 0 can be found. So ms plus 1 minus 1, and then you go to the ms 0. So there are 25 such possibilities. You can write all of them. So 25 of them can be written. So in this manner you have a huge number of tables, large number of tables that you have to maintain, and then you have to again eliminate in a similar fashion that we have considered already. So that one I found that was one easier. But if you like ml values, so chart out the microstates and then enter the total number of microstates having equivalent ml and ms. So after observing all those microstates, you summarize into a third table. So these are table. You can go on writing, or the way I have told you, just prepare one table and get back to the all the microstates. That is also possible. So if you write in this way, again we identify. So we have summarized how many plus 4 states are there, how many ml minus 4 states are there, and corresponding to that, what is the possibility. So here in case of plus 4 and minus 4 maximum values, there is always ms should be 1. It is a paired electron. So now if you start charting out, we can resolve the microstates. We can immediately consider this minus 4 ms 0. Then this so ml plus 4 or minus 4 is possible only when capital L is 4. So it must correspond to G state, and orbital singlet. So an orbital must be in a singlet state ms 0. So 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 we assign this J sorry 1G as the one as a superscript representing the multiplicity, and you will get 1G representation is a 9 by 1 matrix ml by ms, and you can rearrange range from, so sorry, this plus 4 to minus 4 is the range. Yes, so the same thing we are arriving at in a different way already. Okay, so we deduct all of them. So what we do, So removing 9 microstates from table 1. So you see the table 1 you had 1, 2. So removing 9 microstates from table 1, you had you made this kind of table where you can clearly see. So you have 9 microstates removed. So 2 minus 1 minus 1. So all of them minus 1. So like this, minus 1 minus 1. So all of these are the 9 microstates that will be removed. And so you look at the middle one. So then you have 1, 2, 3. So all are arranged in this manner. So this is a new table that you get. Again, follow the same procedure after removal of the 9 microstates, and you can get the 3f term. So ml and ms. So ml next highest is ml3, ms1. So this is ms1. So you consider, so this must be 3f state. So that's plus 3 minus 3 is the maximum. So this must correspond to f state. And again we have possibilities of ms1. So all the three ms values are possible: 1, 0 and minus 1, plus 1, 0 and minus 1. Now it should be, if it is 3 by f, it must be 7 by 3 matrix, 21 microstate to be deducted. So cross out. So what you did in the first table, previous table, minus 1 minus 1, you go on doing this way. So you have already have 7 into 3 minus 1. So all go on subtracting and write a new table. Sorry, not here. This is the representation of ms0. So like that. So new table that you will make will have terms that has gone. So after removing this 21 microstates, you are left with plus 2 and minus 2 as the highest ml. So again follow the same procedure. So now you have 5. So how many microstates to be removed now in the, so we have removed 1g 3f, so total of 30 microstates removed. And there must be hello, namaste. So in this manner you can again see plus 2 maximum here, which has the maximum value of ml, plus 2 ml, ms is 0. And so you start. So this will give you 5 by 1, 2, 3, 5 by 1 matrix. So highest value of ml, ms. Okay, so this is the 1d term and total of 5 by 1. So start deducting the terms. Minus 1, and in this manner you carry on deducting the terms, and you will get 1, 2, 3, 4, 5. So you can sub plus 2 minus 2, 1, 2, 3 minus 1. So when you do this, all these are gone, and now you are left with 1, 2, 1. So now the combination that you have ms. So you have already sorted out 35 microstates. Now you are left with ml1, ms1 as the term. So 3p, which is 3 by 3 matrix again. So 9, again subtract minus 1 minus 1. minus 1. So this will give you, so this will give you only 1 will be left, rest of it will be gone. So corresponding to, so the new table will be this. So 3p, and now you have the so after removal of this 44 microstates, you have the 1s state. So this is how, this is the D2 configuration. We have been able to account for all the microstates. So these are the things that, yeah, we need to discuss, and these are the splitting patterns. So we have already discussed. So atomic energy levels are affected by spin-spin interaction. So that is the first thing that whenever you draw energy level diagram, you take that into account first. Then orbit-orbit interaction, that is the capital L, L1 plus L2 plus and so on. Here it was S1 small s, that's the individual spin, S1 plus S2 and so on. Then spin plus L, so spin orbit interaction, that was J. So J, that is consideration of L plus S, L plus L minus S, L plus S to L minus S. So that is the J values. So these were the interactions of orbital, total orbital angular momentum and total spin angular momentum. Remember, this is a magnetic interaction. You have to treat the two things as magnetic, two different tiny magnets, and then it becomes easier to understand. So this is the J, and these J values can be further split. So Hund's rule 1, and then Hund's rule 2, and finally we have Hund's rule 3 for this J, and finally Landé's interval rule for J plus 1. These are the things. So spin orbit coupling, last point, we have come to the last point, which I will try to finish this for the term symbols with this thing. Spin, the effect of nuclear charge on the spin orbit coupling. So you need to understand this. Imagine yourself to be riding an electron, which you think of an electron orbiting a nucleus like this. So imagine you are the electron and you can see the nucleus. So apparently what it will appear, if you are the electron sitting on the electron, you will see that nucleus is moving around you, like the sun appears to be moving around us when we are from the Earth's frame. Okay, so that is the situation initially. So it will appear to you there is a magnetic field. So when you are riding with the electron, you see a magnetic field that is caused by the relative motion of the nucleus. So this relative motion of the nucleus gives a magnetic field, and that magnetic field will also affect. So this is the point of view. So when you are riding the electron, you will see that as in when your reference frame is that of electron, you will see that proton is moving around. So a moving charge generating a magnetic field here. The classical picture, so we are viewing it classically, and so it should be affecting the overall interaction that was magnetic, L plus S, whatever. So this interaction effective current is given by this, if you generate, so this moving charge generates a current del Q by T. So if you put that number and Z, so it turns out to be ZE into V by 2 pi R. So magnetic field is given by this. So that's why we say that nuclear spin orbit coupling is much more stronger in the heavier elements, where you have a large number of protons are there, and as a result you will see stronger. So as the number of protons increases, there will be greater the number of nuclear charge, stronger the magnetic field. So the spin magnetic moment of electron interacts with the orbital magnetic field, and then nuclear charge also affects, generates the magnetic field, and that also affects the spin orbit, this thing. So as Z increases, the atomic number you saw previously, yeah, sorry. So it so the coupling increases sharply with atomic number as the atomic number increases to the power of 4, Z to the power 4. So that is this due to nuclear effect on the spin orbit coupling of electrons. So heavy atoms, it will be, as I told you, heavier elements, large number of protons are there, and you will see the enhanced effect. So it is only small h giving rise to slight change in energy levels of 0.4 cm inverse in the lighter elements, first row elements, and if you go to the lead, it is 1000 cm inverse, shifts of the order of 1000. So you see the almost more than 10,000 times increase is in the spin orbit coupling pattern in terms of energy can be obtained. If you compare the number of electrons in lead and carbon. So that's it for today. Then you so again selection rules. The one that we discussed in the simple case gets slight modified. We have to conserve the spin of photon, and that gives you so further consideration, which the details of which I am not going into at this point. So we have already discussed it will be similar, and the results will be this. When you consider those things, del S is equal to 0, del L plus minus 1. So at the same time, small del S. So for individual, so overall summation of big L, capital L changes can be changed from 0 or plus minus 1. But for an individual electron, if you look at it, del L must be plus minus 1. And del J can change from 0 to plus minus. So but J is when it is 0, uh, when J equal to 0, that means it cannot J cannot be 0 in that case. So this condition is not for when J is 0. This is not applied. In that case, it must change by plus minus 1. So overall spin, no change in overall spin. That's what we have, del S rule. So that is so because we know now that light does not affect the spin. Del and these two rules are about the orbital angular momentum, and that must change for an individual electron. But in a summation, whether or not this results is overall change of orbital, that may be 0, overall change may be 0, del L may be 0, but for an individual electron, del L must have changed. So that you have to satisfy the summation of L and the small l. So that has to be taken care of. So these are the things. So with this, your term symbols is finished. That is the spectroscopic. These are involved in spectroscopic transitions for multi-electronic system. And so this is done. Quantum mechanics is done, and I will start statistical mechanics. 2 classes. Give me 2 classes on statistical mechanics. I'll tell you about the important things. So that's it for today. थैंक यू. जो भी होगा आप एक बार पढ़ लीजिए फिर से, और लेट मी नो.